Hello and welcome to this Serious Stew Games Lab video. My name is Dr. Chris Skinner. I'm a research fellow at the Energy and Environment Institute, University of Hull. In this tutorial, I'm just going to be talking to you about sea level rise in the Humber Estuary and how that's going to impact coastal flooding, especially from things like storm surges. The Humber is on the east coast of England and it drains about a third of the country's landmass. It's vital to the UK's economy. It's the energy estuary. 25% of the UK's oil and gas products come through its ports, but it's also at the forefront of the renewable energy revolution with wind turbine construction on both sides of the banks, and it's a major hub as well for biofuels. Unfortunately, a lot of the land around the Humber is really low lying, and that means being on the coast, it's at risk of flooding. And as our sea levels are rising, this risk is only going to increase. So during this video, we're going to look at what the risk is today and how that's going to change with sea level rise. So sea levels are rising around the world. This is partly a natural effect. We're still coming out of the last ice age, and over the last few centuries that rise has been about 3 millimeters a year. However, that is accelerating because of the amount of greenhouse gases we're putting into the atmosphere. Those are warming the atmosphere. It's melting ice caps, which is then releasing that ice into water, which is filling the oceans up. But also the extra heat is making the oceans expand and take up more space. And that's also causing water levels to rise. We have lots of really good predictions of how that might affect us in the future. And for the Humber, we use the UK's Climate Predictions 18 to see what will happen in the future. And that's what this graph is showing here. And we've got a couple of different scenarios we can look at. So our first scenario, the blue line, is what would happen if we took drastic action on climate change right now. We drastically cut down all our emissions. We've got a range here which goes from about 70 centimetres or at the very minimum about 30 centimetres. So that's getting back to that natural 3 millimetres a year. So we can limit the amount of sea level rise that will be going into the estuary. If we don't do anything, then the best we could hope for is about 60 centimetre sea level rise. But actually it could be more than double that, about 1.3 metres, 130 centimetres high. So there is a range of different sea level rises we have to consider in the future. But we err on the side of caution when we're making plans for flood defences around the estuary, and we plan for about 1 metre sea level rise in the next 100 years. So a popular method to try and assess what impact this sea level rise will have on areas is to use a free online mapping tool. This one is probably the most popular, the Climate Central tool. And here I've applied 1 metre sea level rise to the Humber. This is a really nightmarish picture, and it provokes headlines by the local media to say things like, the area's sunk, we've got no hope. People are going to have to move out of cities and change where they live. But the problem with this mapping is actually it's really quite basic. It's based on a really low resolution mapping collected from space, and it misses out a lot of details, things like flood defences, or even the fact that water needs to flow in these areas and will get blocked by other things. So we need to use something a bit more sophisticated when we're looking at localised areas like the Humber. And what we're going to do is we're going to use a hydraulic model to actually look at what impact this 1 metre sea level rise has on the area. So this is a version of the model we use. This is a model called Caesar-Liz flood. This one I'm showing you here is actually a really older model. It's a lot low resolution, so I can get it to run nice and quickly. And the main differences between this and the Climate Central map is what we're doing here is we're actually modelling water flows. So we've actually got tides coming in on this right hand side from the North Sea. And those tides are propagating through the estuary, and you'll see the water level go up and down because of those tidal levels. The other crucial difference in here is that we have a representation of the flood defences as well. So water can only flood onto that lower lying land if the water level gets high enough to go over the top of those defences. And this allows us to get a really good picture of what the flood risk is around the Humber. Now using this slider I can raise the sea level, so if I just move that up to 1 metre, we'll see now as we're getting up to the high tide, we see it's now adding an extra 1 metre onto the top of that high tide, and we can see the estuary is really filling up, that water is going right up to the top of those flood defences, but we're not actually seeing a lot of water going over the top. In fact, we're not seeing it, barely any water going over the top. And now that high tide is going down. Another way to look at this would be to look at the data itself. So this is a snapshot of 2 weeks of tidal level data that we used to run the model with. And we can see how the water level varies over the tidal cycle. So we get about 2 tidal cycles a day. It goes up to a high tide, where it's about between 3 and 4 meters mainly over here. And then it goes down to a low tide. And if you go to the coast, you can stand there, you'll be able to see the tide coming in and out during the day. These tidal cycles also have a spring and a neap cycle. So we have these spring tides, which are the high ones. So about 3 days in, you can see the peak of that spring tide, where the difference between the high and the low tide is the greatest. And then sort of between 9 and 10 days, we'll see that's the peak of the neap tide, where actually that difference is the lowest and the tides are lower. Now, if we think our flood defences around the estuary, let's say that they're 5 metres high, we can see that during that tidal cycle, both spring and neap, that the water level isn't great enough to reach that 5 metre level. Now, in 100 years' time, we're going to add 1 metre sea level rise onto these tides. So our tides could then look something like this. Now, the spring tides now are getting quite close to that line, but actually they're not actually going over the top. So therefore we're not seeing any flooding because that water isn't getting high enough to go over the walls. So why do we say that the flood risk around the estuary is getting higher? Why do we say it's getting greater? Why is it increasing? What is causing that flooding? Storms out at sea actually have the ability to raise water levels. That's because the low atmospheric pressures at the centre of these storms actually reduces the weight of the air pressing down on the sea. That causes the water to rebound and the water level to increase. Strong winds also whip up waves and can cause the ocean to swell. That also increases the water level. We call this increase in water level a storm surge, and it can last anything from a few hours to a few days as the storm passes the area. So on December 5th, 2013, the Humber was hit by a storm surge which approached about 2 metres above the normal tidal level. Unfortunately, this was timed with a high tide, so it actually caused flooding around the estuary. But both the storm surge itself is quite rare. We'll probably get a handful of these every winter from storms. And it's even rarer that it will be timed with a high tide. So to demonstrate this, I've taken our 2 weeks worth of data and I've added 2 metres to all of those water levels, which is shown by the red line. Now we'd only get chance of flooding when that red line is above our defence line, which we've set at 5 metres here. So as you can see, this is really only really short windows during really high tides during the spring tide part of the cycle. This actually accounts for about 22 hours of that 2 week period, about 6.5% of the time. If it happened, if we got the 2 metre increase during the neap tide, we probably wouldn't see any flooding around the estuary at all. We'd just see a really particularly high low tide during this time. However, if we got the storm surge occurring after about 2 days in our cycle, where we've got a high spring tide, we will see flooding around the estuary. Now the problem with sea level rise is what that does is increases that window of opportunity for where we will get storm surges. So we'd also expect the storms to become more frequent, but the chances of them being timed with a water level that will cause flooding will also increase. So with a 1 metre sea level rise on that we've got here, we can actually see that that window increases to 84 hours, which is about a quarter of the time of that 2 week period. In order to manage this, what we need to do is actually increase that water level, the defence level, that 5 metre line, to keep it in line to give us the same standard of protection in 100 years' time. We'll have to move that up to 6 metres. So I hope you found this video useful. What I've hoped to really get across is that when we're talking about flood risk in areas like the Humber, we're not talking about areas being permanently underwater by that sea level rise, but actually it's an increasing flooding due to the increasing opportunity for storms being timed with those high water levels enough to overtop the flood defences. I've also hoped that you understand the value of the modelling tools that we use, and how, even though there are useful bits of information we can get from tools like the Climate Central maps, actually to understand flood risk fully we need to have models which actually represent water flows and flood defences in there. Finally, I just want to reassure you that there are lots of really clever, hard-working people trying to understand and deal with this flood risk in areas like the Humber. In particular in the Humber, this is being led by the Environment Agency with their Humber Strategy 2100 Plus. There should be a link up on the screen now. I do encourage you to go to that to see what the plans are to around the estuary to really deal with that flood risk. Now, if you hold on just a few moments, this video will end with a quick guide of how you can download our model and how you can use it on your own computer and have a play with it yourself. But for now, thank you for listening. So I've downloaded the folder from our box file and I've put it onto my desktop. It's here, just Humber in a Box beta. I'll open it up, and inside are all the files that we need to do the modelling of the Humber. The model itself is in this program here called Humber Tides Free. So if we double click that, it'll just open up there. This is the graphical user interface for the model. This is where we put all the data and everything in for the model to run. We have these preloaded, so if we go to config file, and then if we click open, it opens up the folder, the one that we're working from, and hopefully there should be a file in there called config file. This is basically a text document. It just it contains all the information that the model needs, where it can find all the data that it needs to run. So if we click open on, if we highlight that and then click open, it doesn't really look like there's anything in there now, but if we click load data, you'll get 4 warnings on here. You can ignore those, they're just for us as operators, just so we know what's going on. It's loaded in the data, and we can visualize that by going top graphics DEM. So DEM stands for Digital Elevation Model, and it's basically just a map of heights for the different areas. So we click DM, and there we go, there's our height model for the Humber. Now if we press start, the model begins to run and it starts filling up with water. So you can see the shading on the water here. It goes from kind of a light blue, which is really, really shallow, through the purples into a bright pink, which are the deeper areas. So the deepest areas you're looking at here are probably about 26 meters deep of water in some of these channels. So we've got, on the right hand side of the model, we've got the North Sea, and these are the tides coming in and out. And on the left hand side we've got 2 river inputs, the Ouse and the Trent, which are much, much smaller in comparison. We see when the model's filled up, it will begin to model the tide. So the tide goes out, and then you'll be able to watch the water coming back in again. So congratulations, you are now a numerical modeler. You are modelling the environment.